the chat. Okay, Yolanda, if you could go ahead and, oh, we are now live. Okay, great. We are now streaming live. Great. Well, welcome. Hello, welcome to this evening's panel, herding data from space rocks. That'll probably make more sense as we go along. My name is Andy Shaner with the Lunar and Planetary Institute, and I'll be your moderator this evening. Right now, I'd like our panelists to take a moment to introduce themselves. Tell us a little bit about yourself and what it is. How do you work with astromaterials and or astromaterials data? Let's start with you, Minnie.
Well, thanks, Andy. My name is Minnie Wadhwa, and I am director of the School of Earth and Space Exploration.
That'll probably make more sense as we go along. My name is Andy Shaner with the Lunar and Planetary Institute, and I'll be your moderator this evening.
Andy, I think that was something. In any case, maybe I can start over. Anyway, so I'm director of the School of Earth and Space Exploration at Arizona State University, and I'm also the Mars Sample Return Principal Scientist, the program for the Mars Sample Return Program. And I'm a planetary geochemist, I would say. I use geochemical and isotopic data on meteorites and other materials returned by spacecraft to try to understand the early history of the solar system and how the planets, the rocky planets in particular, were formed and evolved early in the history of the solar system. So that's sort of my, I guess, summary of how I use astromaterials, which, for me, all of these materials, samples of meteorites, things returned by spacecraft, these are all of interest, and I like to study their geochemistry and isotope compositions.
Thank you, Minnie. Pierre.
Hi, I'm Pierre Hanukko. I'm assistant professor at the University of Arizona. I'm also a cosmochemist. I'm working on both geochemical and isotope data of both meteorite and return sample, and my focusing particularly on stardust grain and organics. My interest in astromaterial data was related to my work that I'm currently doing on the NASA OSIRIS-REx mission, and the lead working group lead for data archiving and data management for the OSIRIS-REx mission. So we've been really interested in developing software and tools for data management and archiving, and so we are working on developing an app for sample tracking. And so that's the start of the idea of this whole workshop that we're going to talk about today.
Great, thank you, Kerstin.
Yeah, hi, my name is Kerstin Lehnert. I am a senior research scientist at Columbia University's Lamont Doherty Earth Observatory, and there I'm the director of the Geoinformatics Research Group, and I have been building and operating data systems for geochemical data over nearly 2 decades. And in the last 5 years, I have also worked for NASA in building the Astromaterials data system, where we make sure that data generated on the astromaterial samples is preserved and made available to researchers and the public alike for anybody's access, in the expectation that this open access to the sample data really drives future science forward. And I'm very passionate about it.
Great, thank you. And finally, Justin.
Yeah, hi, I'm Justin Simon, and I'm a planetary scientist at the NASA Johnson Space Center in the Astromaterials division. And I lead the Cosmochemistry and Geochronology group. And so I think there's a common theme here that there are a number of us that are interested in the sort of chemical or the isotopic record that we can read out of these astromaterials. And so I work on a range of different types of materials, as our other panelists do as well. Probably the most relevant to this discussion are lunar samples and some of the next generation, the ANGSA samples that are just being opened. I'm also a member of the Return Sample Science group on the Mars 2020 team, and I'm helping document some of the data that provides context for the samples that will be returned.
Great. Well, thank you all very much for joining us. Again, anyone in the audience, if you're on Zoom and you have a question for our panelists, please put that in the Q&A box. If you're joining us on YouTube, you can put a question in the comment box there on YouTube, and that question will get passed along, and we'll be sure to ask it. So everybody has already basically asked kind of one of the first things I wanted to get to, which is what are astromaterials? What are we talking about? What does that mean? And so, simply, it's rocks, samples, things from our solar system that we have here on Earth. So it includes too, but is not limited to everything you've all said: meteorites, lunar and regolith samples, the Apollo astronauts returned, even solar wind particles returned by the Genesis spacecraft in 2004. And you've also gotten to this, but I'll go ahead and just bring and ask you again. So, and we'll start with Minnie, and others are welcome to jump in too. But why are astromaterials important? Why do we care? I mean, we have spacecraft that take pictures and get spectrum, but why do astromaterials matter?
Yeah, so astromaterials really, I mean, thinking about, just as an example, thinking about the moon, for example, I think, we had some degree of understanding of what the moon was made of, and some understanding of some of the geologic features from some of the imaging that was done early on, of course, not to the great detail that we have now, of course, but when we brought the samples back from the moon, that's when we really understood in really exquisite detail some of the geologic and geochemical evolution of that particular body from studying these materials. So that, there's a level of detail that is just not feasible with remote analyses, that astromaterials analyses in laboratories on Earth, with the best analytical capabilities that we have, that we can bring to bear on these materials, they can open up a whole new world of information that is not accessible really with remote analyses. Remote analyses, of course, are complementary, and it's not to say that there's not value to doing that, but I think there's a combination of both of those things that can really help us to advance our understanding of the origin and evolution of the solar system and planets that really it would not be feasible if we were not able to analyze these materials.
Okay, great. Anybody else want to add to that? That was a pretty good answer. All right. So earlier this week at the University of Arizona in Tucson, they hosted a meeting that brought together not just planetary scientists, it turns out, but scientists were invited from other disciplines to come and talk about efforts to manage this, what turned out to be an incredible amount of data that we've collected over 50 plus years now. And with missions like OSIRIS-REx, bringing samples back from the asteroid Bennu and Mars sample return one day, the ANGSA program, where scientists are currently got their hands on these previously unsealed Apollo samples. There's more data being produced and on the way. So when we talk about astromaterials data, what are we talking about? Like, what are the types of astromaterials data? And tell us, what kind of data do you work with in your own research? And then, Justin, I want to start with you.
Sure. Yeah, it's a short and a long question. Answer for that, but. I'll just give some examples of some of the projects that we've worked on. And so you could sort of distill it down to us trying to visualize these materials so that we have some understanding of what they look like physically, sort of the various components and constituents that are in them. And then we target those materials with various different type of analytical techniques, whether they be a chemical technique, and some people are doing structural techniques and things like this that are looking at the materials at an atomic level. So an example from my own research, I talked about the lunar samples and Martian samples, but probably that would best illustrate the use of an astromaterials is actually from a chondrite, which is a primitive meteorite, in which these rocks are actually a sort of an accretion of various different types of particles, and those particles all have potentially distinct stories to tell. And so taking images of these rocks, these meteorites, categorizing what types of components you have in there, and sorting through this haystack, if you will, to look for sort of a common thread or a story that they have to tell about the early solar system. And so each one of those particles provides a segment of that story. And if you can keep them all organized, these data, both in a spatial way, but also in a temporal way, a lot of what we try to do is try to determine the ages or the relative ages of these different materials. We can tell that story more clearly. And so we use non-destructive techniques that allow us to look into these rocks using X-ray tomography. We look at polished sections, whether they're thin that we can see through them, or they're just polished so that we can see an exposure of the fresh surfaces. And then we can characterize these particles. We can, sort of like a biologist might do, we can look at various examples of these particles and try to put together a coherent evolutionary story.
Great, thank you. Any of our panelists want to add to that?
Well, there's clearly also a lot of the chemical compositions with respect to the individual particles that Justin was talking about, and the entire pieces of rock that exist. And there are so many different aspects of chemical composition. You want to know any of the elements in the periodic table, basically, are they contained in there, are they not? And then there are, ways to use the chemical composition to get information on the age of these samples as well. And I'm sure that Pierre and Minnie can talk much better than me about that. But what from my perspective as a manager of these data matters is that these data get better and better over time. More and more information comes out of it. The data grows rapidly. New instrumentation is being invented. And so it's just a fascinating evolution to see how much more data we can extract from each one of these materials to better understand how our solar system and universe have evolved.
Yeah, I heard a presentation from one of the first scientists to look at the Apollo samples when they came back, Apollo 11 samples, Grant Hyken. Heard a really interesting talk from him, and he said one of the things was those samples that Justin's program ANGSA is now just looking at is they did that on purpose. There were samples they didn't open because they knew the technology would be better at someday to get more from these pristine samples. And also to follow up on something Justin was saying, the chromatography and the X-ray stuff at JSC, they're also doing some pretty cool things with samples that are actually online for the public to go see, where you can actually see these X-ray things and you can get in and travel through a rock, so to speak, and see all the different class and things within it, which is pretty cool. So we've heard this idea of the data management has come up a couple times already, and that's what this workshop was all about earlier this week. So to Pierre and Kerstin, what was the motivation for this workshop, to hold this workshop?
So the idea came on initially from the work that we are doing for the OSIRIS-REx mission, because one thing we realized there is like Justin was mentioning, there is such a large diversity of data going all the way from 3D rendering of the surface or the interior of sample all the way down to atomic scale of seeing using transmission electron microscope and looking at nanometer to atomic scale of sample. And so there is a wide variety of scale, there is a wide variety of data format, and there is a way looking at such on a mission where we want to maximize the science return that we get from the sample and make sure that we can have every scientist on the team have access to the data to be well informed on following analysis. We try to see how we could maximize that chain of analysis and that sequence of analysis and provide a way for people to see and manage the data. And so that got us interested in looking at systems that are currently available. And so getting more and more interested in what the planetary science community and then other communities, like you were mentioning, we had people from the biology department or like geoscience side that were participating in the workshop as well. We realized there was a lot of those projects that were happening both across the US but also international. So we wanted to find a place where we could start building connection and synergies between those projects and see how we can, as a community, make a better general, I would say, community-based guidelines or plan on how we should manage, archive, and visualize astromaterial data to try to maximize the information that we can get as scientists.
Great. Kerstin, do you want to add anything to that?
Yeah, I mean, this was a really great summary. It really is about, when it comes to data, it's about finding ways to connect the data and make sure they can talk to each other, because there are so many different systems. So there's also this aspect that for many years now, a couple of decades, I would say, this concept of open science has been so incredibly important to make information broadly accessible so many people can participate in science. It's really a democratizing of how we do science, and that requires that we look for better ways and more comprehensive ways of making these data available. And there have been, over just recent years, many efforts to define principles for this way of making data openly accessible. And what we're talking about a lot is this acronym of FAIR, which stands for findable, accessible, interoperable, and reusable. And these are sort of facets of good data that really you can go on the internet, which today is the communication channel for us all. You can search for something from a given mission, from Apollo data. You can find it, you can access it. It's not, gone away with a researcher who retired, but is in a place where it's safe for a long time. We unfortunately have a lot of examples where data disappeared because the data was never put into a place that is intended for long-term curating these data. So these are very important aspects that become more important as we're preparing for these new sample return missions, and we need to figure out a way to work together as the community. This was a great event that got that started.
Yeah,
I'd like to,
please.
I'm sorry. I was just going to say, I would just like to expand a little bit and completely agree with what Kerstin was saying. But one of the things that's really difficult for us through the time of scientific discovery is to make comparison or intercomparison between measurements or between observations of different generations. And so this type of openness and clarity of how we did things, and specifically how we are referencing them to sort of a known, we call them standard. There are all kinds of different types of standards, but the ability to reproduce your results is a fundamental aspect of science, the scientific approach. And so part of that is having the accessibility to someone else's data set to say, okay, these are the observations they made. Here is the reference point that they had. This is the actual measurements they did, and this is what they got for the reference, so that when I make a measurement of that reference, I can directly compare my hopefully exciting results to those past exciting results.
Absolutely. Yeah, great points all around. And as somebody who does not work with data in any way like you all do, this meeting was still actually really interesting to me. I learned a lot from it, just because it's just something I've never even had to think about, right? But listening to people who have and who do it every day, it was actually really interesting. So thank you for putting this meeting on. And what I want to ask someone, I want to put out to our audience who are with us this evening. Again, if you have a question, you could put it in the Q&A box if you're in Zoom. If you're watching on YouTube, you can place it in the comment box and we'll pass it along. But one thing that I'd like you all to think about between now and the end of our panel, and you can start writing this whenever you want to in the chat box, is think about if you had access to data, to some of this data from Astromaterials, what do you think what would you do with it? Would you just look at it? Or would you maybe analyze some of it yourself? Or would you maybe use it to come up with some kind of artistic rendering, some kind of visualization of it? What would you do? Just tell us in the chat box. What would you do with this data if it was really easy and simple to access and go anywhere and do it? What would you do with it? As real quickly, a question for the Minnie and Justin related to the previous question. But what was your motivation, your own personal, for attending this meeting?
Well, maybe I could start here. In my laboratory, of course, just like Justin and just like Pierre, I guess, I mean, we generate astromaterials data on a daily basis in our laboratories. And, my motivation for attending was because, well, as a community, we are actually, we're moving towards a more open science policy for sharing data publicly. There's really not a good kind of standard at this point. How do we actually share geochemical, petrological, isotopic data? There's, processes by which we actually kind of improve our methodologies. How much of that data do we actually make publicly available? There's a lot of questions about how to actually implement this. And there's going to have to be some kind of, cultural shift in our community as we think about this and grapple with these types of questions. And so my purpose in attending was mainly just to see kind of where our community, as a whole was in thinking about this and how we can work together to, move forward in this direction.
I guess I'll add to that. I had similar interests and reasons to think about these types of data sets. I'll also add, and actually I won't speak for many, but I think that there's a common thread here. We work closely with curators and curations and collections too. And so, we're not just research scientists, but we also have colleagues that are actively every day trying to develop the best ways to store and to maintain the pristinity of these samples. And so there are lessons learned, right? And when we have a dialogue back and forth with these scientists that also are curators, we can help them perhaps understand sort of maybe the most timely science directions, whether it be a certain type of elemental measurement. Volatiles is an extremely intriguing and exciting thing for the moon and Mars right now, right? As well as the early solar system. But that's something that we weren't thinking about. When I say we, I mean the community 40 or so years ago when some of the Apollo samples were being stored and curated. And so, we've caught up. It's not like that we aren't keeping them in the best conditions that we could, but knowing what scientists that are at the cutting edge are concerned about, the contamination control, what have you, there's that interchange and that collaboration that goes on. So I was partly interested in understanding and sharing stories about collection integrity, and new advanced curation, if you will.
Great. Thank you. We've got a question from the audience. Actually, there's 2 or 3 questions here, but we'll shake it out. So this has been touched on a bit by the panel already, but maybe you can expand. A lot of methods for measuring chemical compositions from geologic type samples result in the destruction of the sample. And I'm assuming these questions are related to samples coming back from missions, but will these methods be allowed? How do you plan to minimize sample loss? How are methods / researchers prioritized when it comes to extremely rare astromaterials? And yeah, go ahead.
I can answer that part. At least part of that question is, at least for the mission, the short answer is yes. We scientists will be allowed use techniques that are destructive. The way we do it to maximize the science that we get from the sample is we try to improve the analytical technique so we can use as minimum sample as possible while still having good data or like the measurement that we want to make. That's one aspect of it, to try to really minimize the amount of sample destructed. And on the other side is also we create a sample analysis plan where there is a sequence of analysis that order, in the sense of we start with the most non-destructive, I would say, or like all the technique that don't destruct or don't damage the sample in any way, going down to the most destructive progressively, to ensure that we get all the information that we can before we do any actual destructive measurement.
I just wanted to add, oops. I just wanted to add to this from the perspective of data management. This is actually why it is so important also to preserve data and make people aware of what data exists. So a given analysis is not repeated, and we're not wasting sample by repeating something that had already been done. So we want to really keep a record of everything that has been done, that has already been studied on a given sample.
And on that aspect, one of the things I would say on the mission that we are building that out, but we had a presentation at the workshop on that aspect, is that's helping also with curation, is we are building now, taking advantage of smartphone, that everyone has a smartphone, and now the resolution of cameras on smartphone is becoming better and better every day. Basically, we are building a sample tracking app. So basically, as sample we go to the team and be traveling around the world, basically scientists will use an app on their phone or an iPad to provide information on the condition of the sample. You can get photograph of the sample if there is any damage, any change to the sample that's happening, and all that information then is instantly, it's available directly on the database that all the team has access to, but also curation. So that means the curator at any time can get a notification even if something bad or something unpredicted happened to a sample.
I was just going to add to Pierre's point. Sorry, Andy, just one last little bit, which is all of our return sample missions have the curation of those samples is a major driver in how we go about this data management and the sample management. And we actually have, depending on how much material is being brought back and what types of material, there's a plan for preserving large fractions of that material for a certain amount of time, and that's actually how the ANGSA program came to be. Is that this wasn't the only decision that 40 or 50 years later we were going to open up this one sample, but there's actually a progressive scheme where there's a certain time in which only the mission or the scientists that are active at that point, they only have access to say 20% of the sample. And then as time goes by and they learn more, do the preliminary analyses of the sample, and they then save the things that are rarer, perhaps more sensitive, or maybe there's something that's time sensitive that needs to be measured right away. But there is an actual plan for every time we have samples returned to Earth for this type of scenario.
Great. Very good. Minnie, you want to jump in on this one?
I'm sorry. No, I think everybody said it all pretty well. I mean, I think, obviously these samples, particularly those that are returned by these spacecraft missions, these are an invaluable resource. And these are, I would say, they're irreplaceable, really. I mean, and you're spending billions of dollars to get them here. You want to maximize the science that you get from these. And so exactly what Pierre described, you have to think about it as a set of coordinated analyses on a single sample that sort of you go through a progression of things leading to potentially the most destructive. So you always, when you're doing these types of destructive analyses, you're trying to sort of subsample so that there might be other types of materials that are similar that could be preserved. For example, if you have a little grain, you might cut it in half and save one half for future analyses and destroy the other half, or something like that. So I mean, I think there's plans like that that help to mitigate against the destructive nature of some of the analyses, which are really the destructive analyses are necessary for certain types of data which can't be acquired otherwise. So
yes, unfortunately, but yeah. And Pierre, that I missed the conversation about that app you were just describing. That sounds like a really great idea. Using technology everybody has in their hand or in their pocket at the time. So we have reached the end of our time. I had a number of more questions we could have asked, but this is a great discussion. So I'm happy this has gone very well. And so I want to thank you, our panelists this evening for participating. And I want to thank all of you online who joined us for this, and thank you for your question. And thank you for the comments. These are some great comments we've got over here. I just put one thing here. We've mentioned ANGSA a few times, and you've probably figured out it has to do with Apollo. Well, it stands for Apollo Next Generation Sample Analysis. So if you want to look that up later and see more about it, some really, really great stuff. So thank you all so much again for joining us this evening, and hopefully we'll see you on another panel. So everybody have a good night.
Thank you.